Similarly, as Nicholas Copernicus presented the heliocentric model, one more shocking correction of how we might interpret the universe could arise, igniting a discussion known as the emergency of cosmology. This emergency is set apart by huge disparities in our estimations and comprehension of the universe's key properties, for example, its age, size, and pace of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has intensified this discussion with observations that challenge the existing principles of physics. So, what exactly is this emergency? And how does the James Webb Space Telescope contribute to it? Well, describing it as contributing is a bit of an overstatement. More accurately, it has initiated a significant review of our understanding. The emergency refers to a point where our understanding of the universe is being tested, especially in terms of its age and size, which are connected by an impressive margin of uncertainty. The introduction of the JWST has been essential in this context. Before its advanced capabilities, we were limited in how far we could see into the early universe. Yet, with the JWST's enhanced tools, astronomers can now explore significantly more distant galaxies, providing us with new perspectives on the universe and challenging some of our previous assumptions. This advancement allows us to look further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical data that can either support or challenge our current models of the universe. To understand the emergency in detail, it is vital to examine the standard model of cosmology, known as the hot inflationary Big Bang model or the lambda-cold dark matter, lambda CDM model. This model has been remarkably successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the formation of galaxies. The lambda CDM model posits that the universe began with a Big Bang, followed by a period of rapid inflation, and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every new observation, especially with advanced instruments like the JWST, raises the possibility that our current model may be incomplete or require revision. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we observe in the local universe. This is because heavier elements form in the cores of stars and are distributed through processes like supernova explosions, which take time to occur. Yet, scientists have found isolated evidence that challenges these predictions, resulting in a crisis in cosmology. The emergency of cosmology highlights the uncertainty about the age of the universe. Different measurement methods yield varying results, causing cosmologists to struggle to reconcile these discrepancies. To address this issue, scientists employ several methods to estimate the age of the universe. One method involves studying cosmic background radiation, which traces the history of the universe's expansion and uses mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, to determine the expansion rate and, hence, the universe's age over time. The cosmic microwave background, CMB, a remnant radiation from the early universe, is a critical tool for this measurement. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable insights into the universe's composition. However, these maps lack data on dark energy, a significant component of the modern universe. Despite this limitation, scientists use the Friedmann equations alongside other observations to estimate the universe's expansion rate at different times and ultimately determine its age. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae serve as standard candles because they have a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can determine their distance and, consequently, the universe's expansion rate at different times. This method, used in the 1990s, played a critical role in the discovery of dark energy, which is now central to cosmological calculations. This technique is particularly useful for determining the Hubble constant, a measure of the universe's expansion rate. Although not precisely constant, The Hubble constant is instrumental in charting the universe's growth since the Big Bang, approximately 13.8 billion years ago. Observations have shown that the universe has been expanding steadily. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing the process. Conversely, if the expansion rate is accelerating, it could indicate the presence and influence of dark energy, driving the universe's accelerated growth. In January 2018, scientists found something intriguing. While some telescopes indicated that the universe's expansion rate varied depending on the point of observation, the James Space Telescope measured a faster expansion in the nearby universe, whereas the Planck telescope measured a slightly lower expansion in more distant regions. These conflicting measurements have deepened the so-called crisis in cosmology, as they imply that our understanding of the universe's expansion and its underlying mechanisms might be incomplete or flawed. This discrepancy between the Hubble constant values measured through nearby supernovae, the local method, and those inferred from the cosmic microwave background radiation, the early universe method, has puzzled cosmologists for years. The James Webb Space Telescope, JWST, plays a crucial role in this ongoing investigation. Its ability to peer deeper into the universe than ever before provides scientists with an unprecedented view of the early universe, allowing them to study distant galaxies, their formation, and their properties. These observations help refine existing models and theories, potentially offering clues about the true nature of dark energy, dark matter, and the factors driving the universe's expansion. Moreover, the JWST has uncovered galaxies that appear far more developed than expected for their age, given their distance from us. These findings challenge predictions of the lambda CDM model, which suggests that early galaxies should be smaller, less structured, and less chemically enriched. Instead, some of these early galaxies seem surprisingly massive and mature, raising questions about how galaxies evolved in the early universe and whether modifications to the lambda CDM model are necessary. Another significant challenge arises in determining the universe's age. The standard estimate of 13.8 billion years, based on the lambda CDM model, might need to be revised if new observations continue to reveal inconsistencies. This would have profound implications for cosmology, requiring scientists to rethink fundamental assumptions about the Big Bang, inflation, and the universe's subsequent evolution. The JWST also enables the study of the reionization epoch, a period when the first stars and galaxies ionized the surrounding hydrogen gas, making the universe transparent to light. Understanding this epoch is critical for piecing together the timeline of cosmic history. Observations from the JWST could provide insights into how and when this transition occurred, as well as the nature of the first galaxies and their role in shaping the universe. In summary, the crisis in cosmology represents an exciting yet challenging time for scientists. Discrepancies in measurements of the universe's expansion rate, the surprising discoveries made by the JWST, and the potential need to revise the lambda CDM model all point to a deeper complexity in the universe's structure and history. While these challenges may seem daunting, they also offer an opportunity to refine our understanding of the cosmos and push the boundaries of human knowledge. The next few decades of cosmological research promise to be transformative, as new data and theories continue to emerge. Districts of the universe. This error in estimation features the huge size of the universe and helps us to remember the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Presently, considering the expansion of the universe independently of your location, you would observe the same phenomenon at the same speed, known as the Hubble expansion rate. Initial calculations were based on limited data, but with technological advances, such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Various telescopes use readings of the cosmic microwave background, CMB, to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have been hindered by the discrepancies between these two approaches to determining the age of the universe and its expansion rate. As estimation technology becomes more precise, smaller variations arise, driven by the development of more advanced systems. This progress, unexpectedly, raises further questions rather than providing definitive answers. Although the differences are minimal, just 10 to 20 million years separating the estimates, given that the universe is approximately 13.77 billion years old, it still warrants careful examination. One possible explanation for this error is the potential flaws in our measurements of the CMB. Despite being among the most accurate measurements, it has been extensively tested since its launch in 2003 to validate its precision. Another perspective suggests a possible gap in our understanding of dark matter, raising the possibility that it may change over time and could be linked to dark energy or some other unknown factor. This possibility has led to various experimental studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help address the disparity in measurements. This crisis in cosmology has been further intensified by the discoveries of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST has found objects in the universe that challenge our current understanding. This implies that our scientific knowledge needs a complete overhaul, but the issue is that we have no clear starting point. To understand the scope of this scientific upheaval, we must examine the origins of the universe. Around 150 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. However, these events should be relatively rare. What we do not know is how common galaxies became over time, spanning events between 200–400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This discrepancy suggests that our model needs a significant update. The discovery that the expanding universe depended on galaxies is a major breakthrough. JWST images show galaxies that formed much earlier than anticipated by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms with some helium and residual background. The gravity of the radiation then acted on small perturbations in this hydrogen gas, gradually collapsing them to form the first stars. These early stars, composed mostly of helium and hydrogen, underwent nuclear fusion, creating heavier elements such as carbon and nitrogen. These elements played a critical role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the condensation of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages, including the merging of smaller structures to form larger ones and the ongoing creation of new stars from interstellar gas. However, the JWST has observed galaxies that formed much earlier than expected by our current models.